Bill Clinton, America's favorite president, known for such great things as being the second president in history to get impeached, having an affair with Monica Lewinsky in the Oval Office, and doing marijuana without inhaling in England. Well, his name's not even Bill Clinton, it's William Jefferson Blythe III, but we don't need to talk about the fact that he changed his name, and that's not a cover-up or anything. Bill Clinton with graphs, you gotta use the conic sections, the most important part of pre-calculus, I hope. So, we start off with a circle to find Bill Clinton's head, or most of it, really. Okay, so the equation for that is like 0.7 times x plus 1.65 squared plus 0.7 times y minus 0.56 squared equals 2.8, with a domain restriction of -4 if less than or equal to x or less than or equal to 1.2, and y is greater than or equal to -2. Okay, this draws Bill Clinton's head. So the standard equation for a circle is x minus h all squared plus y minus k all squared equals r squared, r being the radius, h and k being the coordinates of the actual point. So if we look at our actual equation for the circle that makes up Bill Clinton's head, we can see that because we've added a number to the x, that's actually a negative number. So we're going to have our center of the circle be at negative 1.65, and then because we subtracted 0.56 from y, that's going to be positive, so 0.56. So negative 1.65, 0.56. That's going to be the coordinate for our center. And then our radius is, of course, going to be the square root of 2.8, which I can't do off the top of my head. And so the domains were then restricted, so we could like fit it to his head so it didn't look weird and actually covered his hair. And yeah, that's how you make Bill Clinton's head. Next, we're going to move on to everyone's favorite conic section, the hyperbola. So right now, we've got a nice hyperbola making up Bill Clinton's ear of x plus 2.3 all squared over 0.15 squared, which yes, I didn't simplify, minus y squared over 0.2 squared, which I also didn't simplify, minus 3.3xy equals 1. Okay, this one's a doozy. So, much like a circle, the x-coordinate and y-coordinate are both subtracted to manipulate the center in the same way. Okay, that's not a big deal. So, of course, your x is negative 2.3, and then your y is not going to change because you didn't add or subtract anything. The issue lies in the denominators of the two fractions that the two variables sit on that we're manipulating. Since the x is going first, our hyperbola is going to sit sideways, with either end opening to the right and left. Okay, so when we have the 0.5 squared, that is the length of A. A represents the length between the vertex and the center of the hyperbola, which of course the center is what we moved, and the vertex is the start of basically the two parabolas that sit opposite sides of the vertex equidistant that are equivalent to A. Then our second number here is B, which is 0.2 squared, which you don't really have to worry about. It's just the length of imaginary box that sort of changes some stuff, and changes the length of C, which is the difference from the focus to the vertex, which of course widens or narrows out your parabola. The issue here is gonna lie in that minus 3.3xy. This is a tilt of the parabola. Basically, the bigger the number, the more it tilts, the more annoying it gets, and because you're subtracting, it's going to have the bottom part facing down when you tilt it. We didn't really learn about it in this class, so I'm assuming it's not important. Next up, we got those domain restrictions, which are negative 2.141 is less than or equal to x, which is less than or equal to negative 2.114. If these sound like very specific numbers, that's because they are. They were the exact intersections where a line intersects, so I kind of had to use them. It makes sure his ear's all nice, and of course, those x values are restricting the x that can be plugged into the equation, thus restricting how far it can go across the x-axis and the shape of the entire thing. Woo, Bill Clinton. That's his ear. If you like president's earlobes, I mean, I guess that this equation's for you. Now we move on to the parabola, the next conic we're going to talk about. This one makes up Bill Clinton's beautiful, perfect chin. I'm not kidding, his chin is actually a perfect parabola. Like, this isn't a joke. I didn't do anything to this, except move it. So if we look at our equation, y equals x plus 0.72 all squared minus 1.5, with the restriction that y is less than or equal to negative 1.2. Naturally, the domain restriction just means that we're going to cut off how far up the parabola can go. Okay, and then, of course, this one's sort of similar to a circle, so the thing added to the x is exactly the same as h in all of the other equations. So we're going to look at it as 0.72 being negative 0.72, and that's going to be where the x value of the center is going to fall for this parabola, which is also the vertex as the center. It's the same thing. It's not a big deal. Now, the negative 1.5 is actually not negated, so we're not actually adding numbers here. It's actually going to go down 1.5 because when you simplify it all out, you can get to the other form of a parabola, which is, of course, Okay, and you can use the other form of parabola, which makes it more obvious, which is, of course, y minus k equals 4a x minus h all squared. 4a represents p, which is the length from the vertex to the focus, or the directrix. Focus works the same as it would in hyperbola. Closer it is, the wider, farther away, the more narrow. Directrix moves in conjunction with that by the same length. And, of course, the parabola is defined as all the points equidistant from a line and a point, and, yeah, the line's the directrix. Okay, now, his chin, it's great, yeah, whatever. Okay, but why is it perfect? Because if I had added an a coefficient in front of that x plus 0.72 all squared minus 1.5, then it would have been stretched or compressed vertically, and then his chin wouldn't have been perfect parabola. So right now, as it stands, Bill Clinton does have a perfect parabola, and is probably the most perfect man ever created on the face of the planet. So we move on to our big boy Billiam Clinton's nostril. Okay, he's got a really fine nostril. It's like a really good ellipse. Okay, but you gotta understand the ellipse. So if you're looking at the ellipse equation going, that looks an awful lot like the hyperbola equation. That's because it is basically the same equation, except that the subtraction between the two variables that are being affected, x and y of course, is actually now an addition symbol. This makes the, hyperbola parabola things face each other and connect. I don't really understand how this works, but it works, so we don't need to question it. So our equation, of course, for this ellipse is x plus 0.3 all squared over 0.07 squared plus y squared over 0.05 squared equals 1. Now, all of these variables in this equation function almost identically to those in the hyperbola equation. So h and x, you don't need to hear me say those again. Of course, nothing's been done to the y value. The x is going to move -3. Not a big deal. Everybody understands that. Okay? Now, the difference lies in that the fact that the larger number here, 0.07 squared, is a in this case. And a is no longer the length between the vertex and the center. It's now the length between the center and the point that intersects the major axis of the ellipse. So to visualize the major minor axis, just think of splitting an ellipse into fours. Like if it's centered on the XY grid, then it'd be split into fours. The longer axis is the major axis. And then the B in that case is then the length from the center to the minor axis. And C is the length to the foci, whatever. Big deal, woo. Okay, now Bill Clinton's nostril. How did I come up with all of this? Okay, well, I moved it, and then I changed my A and B values to the point where I had a major axis length that I liked and a minor axis length that I liked. Now, the big thing that you're probably noticing here is there's no domain restriction on this. Well, why is that? Because it's a closed shape, and I don't need a domain restriction. Put all those lines together to make Bill Clinton's amazing, beautiful features, along with 89 others or some random dumb number. And you've got this Finna woke portrait of the best Clinton in the world. Sorry, Hillary. This portrait is so beautiful, so lifelike, resembles Bill Clinton in his most prime moment of playing the saxophone on national television for all of us to view, that I'm willing to say even Monica Lewinsky would frame it up and put it in her home. Bill Clinton, a presidential conic portrait. Please don't sue me.